my colleague. We are very happy to have the opportunity to present our project in such a prestigious university in front of other space enthusiasts. So today we are going to talk about Aurora liquid engine, which is the development and test firing of a one-piece additively manufactured liquid rocket engine. More than a simple project, it will be the first engine of this kind to be fired in Europe.
This project is our final year project. We started it with no budget and a blank page. The goal of our team was to answer the following problematics: is additively layer manufacturing viable for a rocket engine? To do so, we developed both the engine and its fire testing bench. We also had a big challenge to gather enough partners from the common industry to conclude this project. We will begin this presentation by resuming the goals and challenges of this engine.
We will then talk about the design of the engine and its architecture.
We will then develop a little bit more about additive manufacturing and how we optimized the engine with this technique.
Then we'll show you how we tested and validated our engine.
And we will finish the presentation by talking a little bit about our sponsors and the future of this project. So first, the goals and challenges. As you understood, this is a one-piece additive layer manufactured engine, which has a regenerative cooling system. We will talk about it later. This engine will be tested next June during a static fire test, which implies to qualify it with both security and safety studies.
So when we had to design the engine, we had to choose the cooling method. As you may know, every rocket engine must have a cooling method or a way to dissipate high temperatures. So if we look at the different methods, we can see the heat sinks, which can be used for small rocket engines, but it's not very efficient.
The second one is film cooling. So one of the propellant is injected inside the engine along the wall, and it will be injected in the nozzle. It won't participate due to the combustion, however, it will produce some thrust by ejecting some mass.
We also have ablative method, which is the adding of a material which will be ablated during the firing.
The last one, the one we chose, is regenerative cycle. So in this method, one of the propellant is injected at the end of the nozzle near the exit area, and it will go up to the combustion chamber through the wall while absorbing the heat of the engine. It will then be injected inside the combustion chamber to burn with the other propellant and produce thrust and gases. This last technique is one of the most efficient ones, but one of the toughest to produce, since it needs many pieces to assemble the whole product. However, with 3D printing, this efficiency is still kept, and it is easier to produce this system. Having this design chosen, we now need to choose the fitting propellants.
So at the beginning, we set specifications about security and safety for the environment and people around when the engine will be fired. So with this, we had to choose propellants which respect those specifications. So we quickly choose liquid oxygen as it is not explosive and very efficient. With liquid oxygen, we could use liquid methane or liquid hydrogen, but as the oxidizer is already cryogenic, using two cryogenic propellants would add too much complexity for a one-year project and for a student project. Besides, their price and accessibility is not compatible with a student project.
Which leaves us with ethanol and kerosene, both accessible and affordable for students. The first one has a lower burning temperature, which means it will produce less heat in the combustion chamber, so it will less stress materials. However, ethanol have a potential risk of polymerization, which could blow the entire engine. On the other hand, we have kerosene. Kerosene has a better temperature ratio. It means that we will need less kerosene to produce the same thrust. It also has a better heat content, so it's more fitting for a cooling system, since it will absorb more heat from the engine. But kerosene has an important disadvantage. It's the phenomenon of cooking. This phenomenon is induced when the engine stops and the leftover propellants evaporate inside the engine and will stuck the cooling pipes. However, since we didn't design this engine to be reusable, we chose the kerosene since it is more compatible with the regenerative cooling system.
After this preliminary study, we started the sizing of the engine. So we were following guidelines as a 1 kilonewton thrust for the engine, specific impulse in the void of 200 seconds, and a pressure in the combustion chamber of 20 bar.
The engine is developed on the ground at atmospheric pressure. So with those data, we started the pre-sizing of the engine using two methodologies. The first one, the most scientific one, was based on NASA and Rocket Lab methodologies and our lesson test. And then the second one, the more engineering one, we listed the similar projects made by other students and passionate people to verify our methodology using their sizing. Once we had this pre-sizing of the architecture, we started to look up for a sponsor who could print the engine with our dimensions. Then we improved the sizing by improving selected models and initial hypotheses.
When we found ADAP, a French company, as our sponsor, we optimized the 3D geometry for 3D printing with their help. Also, we had to optimize the cooling channels and the injection pre-chambers injection cavities here, as you can see. Also, we had to choose a material for the printing. The material that has been chosen is Inconel 718. Very suitable material for high temperatures environments, and it's very used in the space sector.
With this whole process, we have also the final sizing of the engine. Here you can see some dimensions. You can look at this after, but so the engine is about 20 centimeters for its length, and it has 8 injectors of kerosene and 16 injectors of liquid oxygen.
So the most interesting thing about this project in this engine is its structure fully made by additive layer manufacturing. This method allows for a wide range of shapes and designs, otherwise impossible to make or very hard to make with traditional manufacturing methods, especially for the cooling channels and the injector plate, which is very hard to manufacture with a traditional method.
However, like every manufacturing techniques, ALMs, for additional additive layer manufacturing, has its limitation on what can be printed. First, the 3D printed part has to be heat treated in order to release the stress induced by the sequential fusion of the metal layers.
Also, you have constraints about the degree, the angle you can print your piece. For example, you should not exceed 45 degrees of shape, because you're gonna have problem with your print later, or you have to add supports to print the piece.
Another key issue of ALM is powder removal with the chosen process, which is called laser beam melting. This process uses a fine powder around the micrometers, which is later fused with a powerful laser. The powder is deposited on the whole printing area, and only the needed powder is fused, which means there is less powders around the engines, but also in it. So to remove it, it is quite easy in a wide area, but you have to think of an optimal powder removal if you want a clean firing and a non-contamination of propellants. So this powder removal is made by vibrating the engine and flushing out the powder inside the channels with the compressed air, as you can see on the right.
But all these constraints are not impossible to overcome. That's why additive layer manufacturing is so promising. For example, you can manufacture your piece easier, as we take as example the cooling channels, which were easier to implement. But also you can reduce your costs, as it is faster to manufacture your piece. For example, if a typical aerospace piece takes months to make, with 3D printing it can be done in a couple of weeks. You can also build complex shapes on your structure. As you can see here on the statue of the Marianne, which is printed with a very complex structure. For the fun fact, this statue was offered to our French president.
So in order to release, to validate the engine performance and its design, we conducted numerical studies. These CFD studies for computational fluid dynamics were based on solving the equations of movements of the fluid and the effect in the engine. To do so, we used a software called Star CCM Plus and developed by Siemens. To simulate the combustion, you have to take physical parameters, you have to choose physical parameters and models. The relevance of these models and these parameters can change drastically the result of simulation. So you have to choose them very wisely.
So here you can see the combustion profile of the engine when it's fired. On a CFD axisymmetric simulation, this axisymmetric simulation allows to study only a quarter of the engine to save calculations time and to be more precise at the end. Here you can find the pressure profile of the engine. You can see the particular shape of the ejected flow. It's a very common shape for rocket engines fired at the ground at atmospheric pressure. As you can see here, we can see this phenomenon on the SpaceX Raptor engine. The ejected flow has a lower pressure than atmospheric pressure, so it's crushed by the atmospheric pressure. You can also see the shock waves reuniting in one point called Mach disk.
We also ran two studies on internal channels. The first one studied the fuel internal channels. In this study, we set the pressure inside the combustion chamber at 20 bars, and we wanted to know how much we had to inject at the entry to have this pressure. It turns out that we have to inject 24 bars at the entry, so we have 4 bars pressure losses due to the geometry of this channel. On the second study, we studied Planck's internal channels. So the entry of this simulation was the pressure and flow rate at the entry of this channel, and we wanted to know the velocity at the exit of injection. In this, you can see that this velocity increases by 40 times due to a high sections ratio between the entry and the exit section.
Finally, you can see here the timer profile of our engine. We did this study to ensure we won't exceed the melting point of the material we use here in Connell. So we expect a maximum temperature of about 950 Kelvin. So you can see the maximum temperature is located at the nozzle, as the section is way lower than everywhere else in the engine.
So after numerical studies, we also ran experimental tests to validate each component. The first one was an injection test using one of those plates to validate, to calculate the roughness of the material, so imperial 780, using water. One other test was to validate the pressurization system, and we will do later a cold test using water and to validate the whole system, the engine, and its testing bed. So as we said before, the static fire is planned for June. So part of the team worked on the fire testing bench, which main goal is to give the engine the propellants with the right amount, the right temperature, pressure, and flow rate. This bench also pressurized the combustion chamber using a neutral gas, nitrogen, to pressurize both tanks and so the combustion chamber.
the bench test is also gathering as much data as possible. For instance, we have a thrust sensor in the nozzle axis. We have 2 pressure sensors in the tanks to know pressure in real time, and also thermocouple sensors on the external walls of the engine to know temperature during the firing. So an important part of this project was to gather sponsors as their essential for the success of this project. It was quite a success as we had Adobe, which accepted to print our model and to help us with the design. We also had Iron Group, which paid for our safety study and allow access to their site to fire the engine. And our last partner is Air Liquide, which gave us a financial support and giving us access to liquid oxygen, which is a difficult problem to get in France. We also had a sponsorship with our Rocketry Association to make a longer project, which is the development of a sounding rocket trusted by an iterated version of this rocket engine.
So to quickly conclude this presentation, we developed an engine one-piece additively manufactured, which will thrust 1 kilonewton using a regenerative cooling system. We can safely say that it is possible to print in 3D a small rocket engine. However, we can only assume that its performances will be as calculated and simulated since we didn't yet use the static test. Thank you for your attention. We have just a small video of the project to show you, and we will then take some questions.